Hello, continuing our work on the tangents of circles, we are going to look for the following. Find the length of the tangent from the circle to the point 7 minus 5. Now what immediately jumps out to me based on what I know about my tangent lines from a point out to a circle is that there are actually two tangent lines, and yet they're only asking me for one length. Well, what does that tip me off to that I might have already been able to see from my sketches? It's that the length is going to be the same for both tangents. And this is going to be an important point when we're thinking about circle theorems as well. But as always, we're going to draw a sketch to improve our intuition and reasoning for our question. So let's do that. I can see I have the equation of the circle given to me in x plus x squared plus y squared plus 2gx plus 2fy plus c is equal to 0. And I now have my 0.7 minus 5. So that allows me to say, and the center I should say, center of that circle is going to be at minus g minus f. Very important we write down both of these things because we have two things we need to change in order to get to the center. And we know that the radius, again, all of this given to us in the log tables, radius is given by this equation. Let's write down our g, f, and c. So g is going to be half of the coefficient of x, which is going to be minus 2. F is going to be half the coefficient of y, which is minus 1. And c is going to be minus 11. Using that information, I know that the radius then is going to be square root of minus 2 to be squared plus the square root of minus 1 to be squared minus minus 11. And it's very important that we sub in everything in brackets. Under exam pressure, the chances of making a mistake and putting in minus 11 when this is going to end up being plus 11 would be very high. So taking the extra time to write it out properly and pedantically is key to guaranteeing or minimizing the chances of making a mistake, guaranteeing the maximum marks in our exam. So we find that the radius is 4, and we can read off that the center of our circle, being at minus g minus f, is going to be at 2, 1. I now have the information I need in order to be able to do the sketch of my situation. So let's do it. I've drawn in my axis here to save us some time. When you're drawing this on boxed paper or in the exam, you can be a lot more easily accurate than me. And we know that our center is at 2, 1. About here. And I know that my circle has a radius of 4, so I'm going to go up to 5 here. And I know that I'm going to go around to a radius of 4 is around here, and to a radius of 4 is around here, and to a radius of 4 is around here. So I'm going to draw in my circle around those points. I'm 4 units away from my center in each case. I draw in a rough circle. You can use a compass. Obviously in the exams you're going to have your construction set with you, so you can draw in a compass and do this very accurately, extremely quickly. And it's important that we do. And then we have the point x is 7 and y is minus 5. So we come down here. And we draw in our point. And then what are we looking for? We're asked for the length of the tangent from the circle to this point. Well, we know that we have a tangent going this way. Best as I am able to draw it freehand. Again, obviously you have rulers that allow you to quickly sketch your situation more easily. But I have my two tangent lines going as so. And I'm looking for this length here. from my point to my point of contact, from my point to my point of contact. And I recognize that these lengths must be identical. And from our circle theorems, we'll be able to work that out as well. There's something important to our circle theorems, which can link into these types of questions in the exam, which is very important to note here. So my perpendicular distances from my center to my lines are going to be the radius, which is 4 in both cases. What angle is in here? 90 degrees. I have a four-sided shape with two opposite angles adding up to 180. That tells me that this shape here is a cyclic quadrilateral. This point, the point of contact, the point of contact, and my point out here all lie on a different circle. And there are lots of things about cyclic quadrilaterals that we know that could be used as an extension to this type of question in an exam. And having our sketch drawn will massively improve our chances of being able to do those type of questions that connect different parts of the course. But for right now, what information do we need? We need to know the length of this line here. Well, we could go on and start trying to find points of intersection and things like that, but something jumps out at me here. I have a length here, I'm looking for a length here, and then there's a shape that jumps out at me. I know this point here and this point here. What shape have I got? A right angle triangle. And I have a right angle triangle here. And these right angle triangles are going to be identical. So really what I've been asked is a convoluted version of just finding the side of a right angle triangle. So let's find the side of a right angle triangle. I'm going to rewrite my triangle. I'm going to call the length I'm looking for L. So if I rewrite that dashed triangle, what does it look like? I have my points here. This is the center of my circle here. It's my right angle. So my center here is at 2, 1. The point down here is at 7 minus 5. And this point would be the point of contact, which we'd often call P in different questions, but that we don't particularly need, or it's not the easiest way to solve our problem to find the value of P. Obviously, if we had the value of P, we could use Pythagoras that way, but there's actually a slightly faster way in this particular case without finding the value of P, and we're looking for L here. L is the line here. What piece of information can we easily find that allows us to find the value of L? Well, I just need to know the distance between these 2 points, the hypotenuse of my right angle triangle. If I know this hypotenuse, then I just use Pythagoras to find L. And in most cases, that will be the fastest way to solve this problem. So I'm looking, because I've drawn my sketch carefully, I'm able to see that all I need to do is find the distance between 2 points and then use Pythagoras to find this missing length. And I also recognize for an exam style question that I have necessarily got a cyclic quadrilateral in this type of situation. Now, so let's find our distance here. H is going to be the distance between 2, 1 over 2, 7 minus 5. So the distance formula is what I need. And I go to my log tables and make sure that I look up exactly what the distance formula is. I do not want to be losing marks in my exam for trying to do this from memory. The log tables are there and we should use them. And I have my x1, y1, and x2, y2. Subbing in 7 minus 2 to be squared plus minus 5 minus 1 to be squared ends up working on down to root 61, which doesn't work out particularly nicely, so I just left it as root 61, and that is equal to the hypotenuse of my triangle. So I now know that that is equal to root 61, and then just using Pythagoras, I have h squared is equal to a squared plus b squared. Whichever version of that you're comfortable with, h squared is equal to root 61 to be squared is equal to 4 squared plus L squared. So 61 is equal to 16 plus L squared. L squared is equal to 45. And L is going to be equal to the square root of 45. We recognize, or take the square root of both sides to write it in for completeness. We recognize that this is 9 by 5 is 45, so I end up with 3 root 5 units for the length of L. When I'm taking the square root here, I don't need to worry about plus or minus the square root because I am dealing with a physical length, and we don't tend to deal with negative lengths. So that is my length of my tangent. And again, I only have one length because this shape here, this right angle triangle, is congruent, is the same as the other triangle that I've got here. This tangent length is also L. There are other ways of solving this problem, as I say, finding the value of P by looking for intersections and so on, but this is usually the fastest way, and if we draw a sketch, it's a method that it is fairly easy to follow and figure out. So that is what we need for finding the equations of tangents to circles and working with tangents to circles.